Welcome to this quantum security and defense presentation, Detecting Graph Characteristics Using Quantum Programming. And thank you for being a valued member of our community. Khrystyna Gnatenko is a distinguished theoretical physicist with expertise in quantum information, quantum computing, and the fundamental problems of quantum mechanics. She earned her PhD in 2016 and her DSc in 2020 from Ivan Franko National University of Lviv. Currently, she serves as a professor at the Professor Ivan Vakarchuk Department of Theoretical Physics at Ivan Franko National University of Lviv. Khrystyna is also a quantum computing research advisor and senior researcher at SoftServe Inc. Her accolades include the 2024 Talents for Ukraine grant, the 2023 Ukrainian L'ORÉAL, UNESCO Award for Women in Science, and multiple other recognitions. Khrystyna actively contributes to advancing science as the chair of the Expert Council for Physics, Nuclear Physics, and Astronomy at Ukraine's Ministry of Education and Science, and as the scientific editor of the Ukrainian Journal of Physics.
Thank you. Many thanks for the presentation and for the fascinating possibility to present the scientific results for you. So we will discuss graph properties and studies of graph properties with quantum programming. So I'll share the screen right now. And so can you see the presentation? Yes, very nice. So currently I am in Lviv. So I'm working as professor at the Professor Ivan Vakarchuk Department for Theoretical Physics at the Franko National University of Lviv. And as the title of my presentation is Detecting Graph Properties, Graph Characteristics with Quantum Programming. So the plan for our presentation is the following. So first of all, I would like to introduce the notion of quantum graph states. What do we mean if you consider quantum graph states? Then, of course, the fascinating property and very important property of quantum states is entailment. So we will discuss the entailment of the quantum graph states and the relation of this entailment with graph properties, of course. Then many graph properties such as number of triangles, the sum of the products of weights of edges, and other interesting things you can see in this presentation, in this slide. So all these properties we can calculate with quantum programming. And the last slides will be devoted to the results of quantum calculations on real quantum devices. We use IBM's quantum devices, but also quantum simulators, of course. So let's start. So if we say the word graph, we mean that we have a structure, mathematical structure made of vertices or nodes and links between them. So in our daily life, we can see graphs like in social processes and in networks of cities and so on. So we have different, wide usage of graphs in our daily life. So different complicated structures can be described as graphs. And these mathematical objects have various characteristics that are important to tell or to answer on the question, do we have a stable graph or not, and so on. So let us find the way how to calculate these properties of graphs with quantum programming. In quantum mechanics and in quantum programming, we have to work with quantum systems, and quantum systems are described with quantum states. So we have various quantum states, and I present here just few of them. So how can we create or construct the quantum graph state, and what do we mean if we have quantum graph state? Quantum graph state is a quantum state that can be represented by a graph. That's very clear. So if we find a representation of our quantum state with a graph, so we find or create this mapping of quantum mechanics to classical one, because graphs, if you consider graphs like a social processes or some transport systems, we have classical systems, of course. So if we find this mapping, we create quantum graph states. And as I'm a scientist, and as a scientist, I can create different mappings, and I can construct the various quantum graph states. So first of all, before presenting the results of our research studies, I would like to note that it's quite important to study quantum graph states because they are highly entanglement states. So entanglement is a critical and important resource of quantum programming. So we use this entanglement in our quantum algorithms. We prepare entanglement states. Then, for instance, quantum graph states are used also in quantum algorithms, also in quantum machine learning and other algorithms. Also, if you consider QAA quantum algorithm, we also have their preparing of quantum graph state. And so the first two things, they correspond to the quantum properties, quantum algorithms. And the third one corresponds to the classical properties of graphs. So from the other side, we can study graph properties with quantum programming, with the help of relation, quantum characteristics, quantum properties with characteristics of graph. So, as I said previously, there are different ways to construct the quantum graph state. In our studies, and not only in our studies, it is very convenient to consider the following mapping. So if I have such a simple graph, so we have 4 nodes and the links between corresponding nodes, I can represent this graph, which is constructed of 4 nodes, with 4 qubit quantum state. So I have to say that for each node in this graph, I have to use a qubit. I have the following numeration. So for this node 0, I use qubit 0, q0, and so on. Then, if I have links between these nodes, I hope I have to also represent these links with some quantum protocol. So we use 2 qubit gates to create entanglement between these quantum states of qubit q0, q1, which corresponds to the link between these nodes. So this is maybe the last slide of the introduction and of the notion of quantum graph states. Then what about results? So we considered various quantum graph states constructed with different quantum protocols, 2 qubit gates. Why do we do this? Because it is very interesting from the scientific point of view to detect the entanglement of quantum systems. In this case, for instance, we have Eisen model, spin system with Eisen model, and we have quantum state, which is quite general quantum state. And with this quantum protocol, we construct not just simple graph, but directed quantum graph and weighted quantum graph. So in this case, for each node, for each link, we have a corresponding property, which is called the weight of this link, and we have the direction. So this quantum graph state corresponds to this, for instance, this graph. And in general case, for arbitrary graph, we found the analytical result for entailment. We considered the geometric measure of entailment. It's very interesting that this entailment, this quantum property, is related with this classical one. So here we have the number of links which ingoing to a vertex and outgoing from it. So this is classical properties graph. And we studied these properties with quantum programming and found the following results. So here you can see the rows, and here you can see the results of quantum calculations. The crosses corresponds to results from quantum programming, and we can see this entailment and dependence of entailment on the parameters of quantum states. So if it is interesting to you to find more information about the studies, you can see these papers, the recent one and the paper published years ago. So we studied different graph states. Then, what about other properties of graphs? What about the sum of products of weights of edges? What about the number of squares, of the number of triangles? So the algorithms we proposed are based on studies of the geometrical properties of quantum graph states. So all these things are related with the geometrical properties of quantum graph states. So you can see this in this slide. You can see the results of analytical studies and the relation of these quantum characteristics with all these properties. And all these things can be found with the help of studies of the operator of evolution of spin system. For instance, spin system, which can be described with Eisen model. The quantum protocol for these studies is presented here. These are results of studies on IBM's quantum device. Error bars and dots corresponding to the results of calculations, and the line represents the results of theoretical studies. So the algorithms, we hope that the algorithms open possibility to achieve quantum supremacy in future in the development of multi-qubit quantum computers. And because all these properties are important in classical world for studies of graphs, so this algorithms open possibility to solve these problems, to study graph properties which are important in logistics and so on, other problems. So more details you can see also in these papers. The recent paper and the paper published with Professor Vakarchuk and Hanna Laba. And the last slides from my presentation are devoted to just short presentation of what do we have in Lviv currently. So we have educational programs, quantum computers and quantum programming. So we have 5 years of these programs. This year we celebrate 5 years of these programs. We have many clever students that study quantum computing, quantum information, quantum programming, the frame of this program. So thank you for your attention. Maybe you have some questions, comments. We'll try to find answers on some. So thank you.
Thank you so much. Thank you so much. If anyone have a question, you can speak up or you can write it in a chat and then I can read it. I have a question because it's those graphs, I mean, they are becoming very important also for defining the quantum internet for the future. And they also coming into play for optimization of like 6G. Could you comment on the power? I think that's very important to discuss that despite that they sound very theoretical, they have immense practical applicability because of that mapping that they really relate to real representations, right? The classical representations of many problems.
Yes, sure. Many thanks for this question. So we can relate these graphs also for studies these networks because for each node we can find different representation. It can be like a computer of a user, so node can be represented with or some internet point, and for instance, it is very important to know the stability of such graph. So if we have problem with some node, what do we have with the whole structure? With the, do we have the same possibility of networking or so on? So the knowing of number of triangles and squares, all these parameters which are called these weights of directions are important for solving these classical problems. So yes, the answer is yes. So we can use this algorithms for such studies in this direction.
And how those instabilities... Yeah, I also wanted to ask you what actually those instabilities refer to in the real life problems. So is there some kind of mapping between those instabilities and actually what it means in the classical
sure.
map?
Yes,
yeah,
I can explain. Maybe it's more clear. It will be more clear if we have, for instance, transport system of a city, and for instance, some station, which can be described by a node, has some problems. So we have no possibility to stop there or to move to the station. So this means, from the point of graph, that we have to remove this node from the graph. And the stability, the question of concerning the stability, can be understood in this case as follows. So, what is the changing of the system? So, what is the changing of time of my travel from point A to point B in this case, if I escape one node, if I escape one station, for instance, or what is the connection between point A in the city and point B in the city if I destroy some links, some roads in the city. So this means that we have stable or not stable. So if we develop this graph, for instance, graph corresponding to the travel system in a city, we have to check all these situations in order to not to have collapse in future. So of course we have to find different ways to different places in order to make this graph stable, in order to find this way from one point A to point B in different situations. So this means.
So in principle, because it has this capability of removing unstable nodes, then in case, let's use that traffic example now that you did it because I think it's very easy to imagine. So let's say there is a traffic jam, right? And then a road is completely blocked, is taken off, and you can take out the node, and then you can still try to recalculate the optimization of, let's say, usage of the road or traffic. So you can, do I understand correctly how that would work, right? In the real time, that would be the advantage of those, that they could constantly adapt and analyze.
Yes, and the number of triangles, number of squares is quite important in this road map of the city, because if you have triangles, so you have two possibilities to achieve point A, for instance. If you have square, you have also two possibilities, and these numbers of this some kind of abstractical things of triangle. What does it mean? We have triangle, but to calculate triangle, it's very, very, it's complicated. For instance, you have this graph, maybe not this, and not this. Like, let's consider this one. So you have triangle, this one triangle, you have triangle between these nodes, and so on. So to calculate this number, you have to check for each node, do we have triangle or not? So from the mathematical point of view, these numbers of triangles is related to the stability. So the stability means that if we have this collapse, if we escape, if we cancel this link, so what do we have great big changing of different other characteristics, for instance, possibility to find the way from point A to point B, or these properties will be stable. So this we call stability of graph.
Thank you. There are some questions I'm gonna get in the chat. I'm gonna read them to you one by one, okay? So did you have from Fred, did you have already a physical test possibility to see the stability?
Currently, no. So we are working on this. So the consideration. No.
That was the last one. How do your results compare presently between the emulators, digital and quantum, as HPC, high performance computers, evolve? Will that gap continue?
So the errors, gaps can be seen from this slide. So here we have the results of real quantum calculation on IBM's quantum device. And the errors bars, I calculate these errors taking into account the statistical error and also the gate error and also the measurement error. So we studied these problems. What about from studies of multi-qubit quantum graph states or graphs with complicated graphs with many nodes? So we checked this quantum states. We tried to run these algorithms for more complicated graphs, but unfortunately, because of quantum errors, we did not obtain correct results. So in these studies, you can see these angles that are close to zero. So we have to study this evolution close to zero. So we need very accurate measurement. So if I understand correctly the question, so this is the answer. Maybe.
Yes, and I think the follow-up to that question was also to ask about that the Google, let me check that I don't mess it up. Yes, that's the continuation. So that's also from Bill. The example was that he's giving is Google HPC's cloud now has the ability to accelerate Kubernetes clusters with NVIDIA's GPUs.
Okay. So we didn't use this. So I don't know. I cannot answer this question because I didn't use.
And then the last question from the chat is, how are these results related to the distribution node degrees through the network?
Very nice question. So I have answer on this question. So direct answer. So we have result. This result is in the case of weighted and directed graphs. But if we have simple graphs, so if we have just vertices links between them, so each node or vertex can be characterized with a parameter which is known the degree of vertex or the degree of node. And the entailment is directly related to this property. So we can find this property just calculating the entailment. So the more details can be found in this paper, for instance, but also in other papers.
Thank you so much. Thank you much. Thank you very much, Khrystyna.
Thank you for watching this presentation, and thank you for being a valued member of our community.